Hey guys, in this video we're going to learn a little bit about Gauss's law. We should already at this point be familiar with the equation from Gauss's law and what each of the things in it refers to, or at least passingly familiar, such as you should know that's the symbol for flux, and that that's flux and that's flux, since both sides of the equation represent flux. But in this video we're going to focus more on the question of how do we use Gauss's law, not to calculate flux, but to calculate the electric field? Because after all, that's really the point, is let's use Gauss's law to find the electric field that exists due to some kind of a charged object. Also, please recall the only kinds of objects that we are going to ever analyze with Gauss's law are going to be spheres, cylinders, and planes. All right, other things that we're going to talk about, though, are some of the conventions that I'm going to use throughout this video. Very often, there's going to be a big deal made about the difference between little r and big R. Little r is always going to be the radius of the Gaussian surface, whereas big R is the radius of the object that you're attempting to analyze. Since the Gaussian surface is imaginary, and therefore any size you want, whenever you see little r, that means that it is a variable. Big R, on the other hand, is the radius of the charged object itself. That is a constant, because the object, of course, has a fixed size, whereas the Gaussian surface is limited only by your imagination. Okay, that's a little cheesy, but you get the point, or at least you should get the point. Little r is a variable. It refers to the Gaussian surface. Also, the A in Gauss's law very specifically is the surface area of the Gaussian surface. Also, please note Q enclosed is the charge inside of the Gaussian surface. Throughout the rest of this video, you're going to see me referring to those two terms and specifically using those operational definitions of them. So pay attention during this part, and if you need to remind yourself, go back to it so you make sure you understand what we mean by A and what we mean by Q enclosed. The object that we are trying to analyze is a sphere. There it is, or something like that. All right. And part A says we're supposed to find the electric field at a point inside of the sphere. All right, so like let's say at that point right there. All right, my Gaussian surface that I would use would be a sphere concentric with my object. All right. And so there it is. My Gaussian surface is the dotted red line. It's also a sphere, and it's supposed to be concentric with my actual sphere. As you should recall, again, from watching the video about cylinders, the A on the left side is the surface area of the Gaussian surface. Therefore, when I use my formula of 4 pi r squared, because it's a sphere, the r is going to be... All right, now I'm throwing this question out to everybody here. Big R or little r?
Little r.
Little r. It's always a little r on the left side. Always a little r on the left side. Every single time, it's a little r on the left side. What, is there a time when it's a big? There is no time when it's a big R on the left side. Absolutely none. Always a little r, because the left side is all about the Gaussian surface. It's not about the object. It's about the Gaussian surface. A is the surface area of the Gaussian surface, and it's any size I want. Little r, therefore, is what ought to be used, because little r is the radius of the Gaussian surface, which is a mental construct and any size I want to. Therefore, I use that variable of little r. Okay, all right. E... Okay, on the right side, Q enclosed. Okay, for Q enclosed, we have to decide if we're using rho or what, okay? The sphere is described up in the prompt as being non-conducting. That's a really kind of backwards way of saying that it is an insulator. Okay, so since it's a solid insulator, what charge density could we use here?
Is it rho equals Q over V?
Yeah, we would use rho. All right, so by way of reminder, rho is Q over V. The only circumstance where you use rho is if it is a solid insulator. Okay, this is a solid insulator, so we would use rho. I know it's an insulator because it says non-conducting in the prompt. And it also says that the sphere is uniformly charged, meaning like throughout its volume. So there's no like holes in it. It's not a shell or something. It's a solid object. All right, so yeah, we would use rho. All right, look at the equation over here. Rho is not a charge. Rho is a density. So if I solve that equation for Q, what is it?
Rho times V enclosed.
That's it. Rho times V enclosed. V enclosed. So that would be only the volume of the object which is enclosed by my Gaussian surface. So that's this, which, as you should recall, that bit had a radius of little r. That's objectively hard to read. Had a radius of little r, okay? Big R was the radius of the entire object, okay? Little r was the radius of the Gaussian surface. So when I do my enclosed volume, formula for that is volume of a sphere, 4/3 pi little r cubed. Okay, should I use big R or little r for the volume enclosed?
Little r.
Little r, yep. Yeah, the radius of the enclosed charge is actually identical to the radius of the Gaussian surface. Okay, I'm only enclosing as much charge as is inside the Gaussian surface, so correct, I would use the little r. All right, and then rho. Yesterday, or whenever you watch the videos about cylinders, we just left rho as rho, and that was perfectly acceptable to do for a cylinder. With spheres, they have a quirk. Nothing I can really do about that. The reason there's a quirk is because in the prompt, they're always, for a sphere, going to tell you the charge is Q. At no point does it talk about the charge density. It doesn't include rho anywhere in the prompt. Therefore, you cannot have rho in the answer. You have to put the answer in terms of the things that are given in the prompt. Now, the reason that they will just leave rho in the answer for something like a cylinder is technically for Gauss's law, it's like an infinitely tall cylinder in order for the problem to have sufficient symmetry to make Gauss's law be perfectly applicable, all right? Okay, obviously there's no such thing as a truly infinitely tall cylinder, but that's the approximation that we make, is that it may as well be infinitely tall. And if it's infinitely tall, then it would have an infinite amount of charge. And so therefore, the density functions are allowed to be in the answers for objects like cylinders and also planes, because for both of those, they just say it's an object of infinite extent. Okay, as hokey as that is, that's what they do to make the math work. Well, with a sphere, spheres have definite, have a definite radius and therefore a limited volume, and therefore you can express Q in the answer. And therefore you can't have rho in the answer. So let's go back over here. Rho is Q over V. So here's the quirky thing that you have to do for cylinders. You have to replace rho with Q over V. The Q and the V in question, though, are the total charge and the total volume. All right, now if I want to express the total volume, which radius would I use for the total volume, big R or little r?
Big R.
Big R is correct. Yeah, little r is just the radius of the Gaussian surface. That's as you can see over here, that's not the total volume. The total volume would use the radius of big R. All right, so yeah, 4/3 pi big R cubed. Okay, all of this work that I've done right over here, all of that is to sub in for Q enclosed. So right now it looks disgusting. However, a lot of stuff is going to cancel. What's going to happen with the 4/3?
Cancels.
Cancels, right? I mean, you can see I've got a 4/3 down here, a 4/3 out there, that's going to cancel. Oh, the pi cancels. Okay, the r's don't cancel because they're different r's, right? Little r is the radius of the Gaussian surface, big R is the radius of the object. So when all is said and done, Q enclosed simplifies to Q, meaning the total charge, times little r cubed over big R cubed. Okay, so all of that was Q enclosed. Let's put it all together now. Okay, all right, and now we're actually very close to the answer. All I have to do to find E is just divide both sides by 4 pi r squared, and we got it. All right, I'm going to put a box around that because that is a perfectly acceptable answer. Now, there is one thing that we could do to, I would say, simplify it and make it look a little bit nicer. Does anyone remember what the relationship is between K, Coulomb's constant, and epsilon naught, that permittivity of free space number?
Isn't it just 1 over 4 pi epsilon naught?
That's correct. 1 over 4 pi epsilon naught. Okay. So that means actually that I could rewrite this expression, I would argue more simply by saying that it is K Q little r over big R cubed. I like that better personally. It's not necessary, right? You could stop right there and that would be good. Okay, but it's, I think, easier to type in if you've got to calculate it to turn it into this expression here with K. Part B wants to know the field outside of the object. That ends up being a lot more straightforward, right? Outside of the sphere. All right, so let me draw my sphere and outside. So now my Gaussian surface is, once again, a sphere, concentric with my real object. But because of its location, Gauss's law suddenly becomes incredibly easy. My left side, the A, is, as before, going to be 4 pi r squared. The left side really doesn't change, right? If you're analyzing a sphere, it's always E times 4 pi little r squared. All right, for the right side here, Q enclosed. I could go through all of the shenanigans again with like rho and charge density and all that. But if I think a little bit harder, I should be able to look at this and say, well, look, the sphere has a charge of Q. How much charge am I enclosing?
All of it.
All of it. I'm enclosing Q. That's the whole thing. So for Q enclosed, I can literally just say Q. I don't have to even use a density function. It's just Q, and we're done. That's what Q enclosed is. All right, so Q over epsilon naught, and that means that the electric field outside of a sphere is Q over 4 pi epsilon naught little r squared. Or, if you prefer, since K is 1 over 4 pi epsilon naught, that is KQ over r squared. Wait a minute, hold on. KQ over r squared, I know that formula. That was the electric field of a point charge that we used like over the last 2 homeworks. Yes, actually. What Gauss's law is telling you is that spheres are point charges as long as you are outside of it. The electric field is the same as for a point charge as long as you are outside of the sphere. Right? So it doesn't really matter what the radius of the sphere itself is, right? It could be a pretty big sphere or a very, very incredibly little sphere, like literally a point charge. As long as you are at a point outside of that sphere, the electric field is going to follow the point charge formula. Okay, so yeah, that's the electric field outside of a sphere. All right, so what we had from before then was electric field inside of this conductor was that. Electric field outside is just KQ over r squared. Let's see. Okay, part C. Suppose that the sphere were a conductor, and then it wants to know how that would be different. Okay, conductor. All right, how would the answer change if this were a conductor? What's the electric field inside of a conductor, guys?
0.
Sure is. Because all the charge on this sphere is, I drew all those pluses there to reflect where the charge lives on the conductor. It's all on the surface. So therefore, there is no field inside of it. Electric field inside is a 0. Okay? All right, what about electric field outside? Would any of my work that I did here change? I think probably everyone's thinking, I feel like it ought to be different, but no. Tom, was that you that said no, it's the same?
I mean, I was going to say sigma instead of.
Right. If you had to use a charge density, yeah, you'd use sigma, right, instead of rho. But the fact is, the charge on the sphere is still q, right? So you're enclosing still just q. So the q enclosed is still just the total charge of the sphere q. So actually, literally nothing changes, right? If you were using density functions, you might get an answer that, say, looks different, but we don't even need to use a density function if we are outside of a sphere, right? Total charge is just q, and so we're done. There's nothing different about the work. All right, so yeah, the electric field inside the conductor is 0. Electric field outside is exactly the same expression as what we got for the insulator. All right, the last part of this wants you to make a graph of electric field versus R. Up to you how you want to do this. You could do 2 separate graphs, or you could do overlaid graphs. So I'm going to do it overlaid to sort of emphasize the similarities and differences. Let's say that we will do the insulator in, I'll do it in blue, and we'll do the conductor in green. Oh man, I don't know about my color scheme here, but we'll see if this works out. Conductor. Oh, that's hard to read. Okay. Okay, so we'll have on the vertical axis here, electric field. On the x-axis, R, distance from center. And I'm going to label one point on the axis, which is big R. All right, so the graph here that we're trying to draw is a graph that shows how the electric field due to this sphere changes as you move from the center of it outwards, right? So as we move out towards the edge, what does the electric field do? Does it increase? Does it decrease? What's it doing? And then as we continue to move on away from it, again, like increase, decrease, whatever. Okay, let's start with the insulator. The insulator equation for inside of the sphere looks like a hot mess. Oh my goodness, there's a K and a Q and all these things. It's not actually at all complicated. You got K, that's a constant. Q, that's a constant. Big R, also a constant. If all of those are constant, then you can look at that equation and essentially treat it like it's, I don't know, I'm going to make up a thing. Y equals 2x. Well, okay, instead of Y, I mean E, right, the electric field. I'm getting that from the fact that R, it's just R. It's not R squared, it's just R, and it's in the numerator, right? So this is a linear equation, right? So it is like just Y equals 2x. If I said, guys, graph Y equals 2x, you wouldn't look at that and panic, right? You would say, oh, Y equals 2x, are you serious? This is honors physics, right? You would just draw me a nice straight line. That's what you would draw. Oops, I didn't quite nail it. All right, now, that straight line reflects the linear nature of this graph, or excuse me, of that function. That function only applies while you are inside of the insulator. This position on the graph is indicating the edge of the insulator. After you leave the insulator, you now have to switch functions. So now we're going to be graphing the E outside function. What does a graph of like Y equals 1 over x squared look like? Anyone remember what that one looks like? What should happen to the electric field as I get further and further away from the sphere?
Decrease?
Should decrease, yeah. As you get further away, the field gets weaker, right? Okay, I mean, that's true for pretty much any charged object. As you move away from it, the field gets weaker, right? So 1 over x squared looks like that, basically. it asymptotically approaches 0, right? So never quite hits 0, right? Asymptotically approaches it. Okay, and so that is the stereotypical graph for an insulator, right? If you're inside the insulator, the field is going to be increasing as you move away from the center until you reach the edge, and then as you move past the edge and away from it, the field is going to decrease, decrease, decrease until when you're very far away, it's basically 0. Okay, electric field for a conductor. Inside of the conductor, the field is 0. Here's how I will graph 0, 0. Gone, all right? All right, and then when you're outside of it, it's that same function, kq over r squared. So at the second you move outside the object, the field goes jump way up, and now it's this exact same thing. All right, so both of them, when you're outside of it, produce the same exact shape of electric field graph. Inside of them, then, is where the difference is. For any conductor, it's going to look like that, right? It's going to be 0, flat line, and then suddenly jump up. For inside of an insulator, it's going to be most likely that linear function right there until you reach the very edge of the object, and then after that, it starts tapering off according to that function there.